So I'll start just talking about what is the problem that I'm interested in dealing with. I don't know if you've seen this video before. So the robot is tidying up. Some bits to know is like this magazine here is a bit tough. He has to take a few tries to get that magazine off the table. It's growing a bit. This is speeded up actually from the original, you can probably guess. But the manipulator clearly knows when the properties of these things, like the magazine, how it bends, and it takes a few efforts sometimes to push a thing into the right position, but it manages to find a way. So in general, that kind of shows you the hardware is not a problem, because without any special tactile sensing or soft manipulators, just with these basic manipulators, a human controller is able to do a very good job of tidying the room. So it seems that humans are very strong cognitively. They don't need to rely on all this tactile feedback and very good sensors. Of course, they do have a good vision sensor to see what's going on in the room, but there's a lot of cognitive ability displayed there in terms of being able to cope with things that don't go quite right in the manipulation. Sometimes it tried to pick up some of those toys and it couldn't get it and had to push it and knock it over and eventually get a place where it can find some surfaces that it can pick up. It's speeded up, maybe you don't see so clearly, but there's a lot of trial and error. So this is what humans are good at. Humans make good guesses about effects of manipulation, like when there's a magazine there that it will bend, you can push it off the edge, you can grab it, then you can pick it up, and how you can lay it on top of another object. And also there's a lot of auxiliary skills, like the little pushes that you do, maybe to push the magazine a bit towards the edge of the table so you can get a better grip on it and to straighten things up. These are what I would call auxiliary skills that humans probably developed when they're babies and toddlers, just pushing and playing around with objects. And robots often are not programmed with those kind of auxiliary skills that don't have a particular purpose, but will help when things don't go according to plan. Some extra manipulations you can do to bring things back to where you want them to be. So those kind of things help you to transfer to new scenarios. And this is mainly what I'm interested in, is robots not in the factory setting where everything is controlled, but when you go to an unconstrained domain, like robot doing something in your house, in your kitchen, and unexpected things will happen. So this is the long tail chart that has been talked about in this article from 2015, but a common idea. So what's happening here is, I'm going to use this, I think, to point. Sorry, it's this middle one. Yeah, sorry. Yeah, so this is the main part of the action. Like these are the main things that happen are in the head, and these are things that happen frequently, and when things go according to plan for the robot, according to how it's been programmed. But then sometimes you get rare things that happen. So the rare things individually are quite rare. Each individual thing happening here is quite rare, but when you add them up, you get a very long tail. And the point they make in this article is that what we often see with AI comes and tackles a new problem, like something in language processing or something in computer vision, and very quickly you get rapid gains, and they're getting up to 70% accuracy or 80% accuracy, and then the gains start to slow down. You see it with things like autonomous driving as well. You find these edge cases, they're not easy at all. They prove to be exceedingly difficult, and you train and train more and more and more, and you get maybe an extra 1 or 2%, and you're never getting up to human performance for tackling all this long tail. So the question then is, how can humans do it? How is it that humans who practice a certain amount when they're children, when they're growing up, how can they tackle unexpected events? And it seems the one trick that humans are using is they use analogy. They hit something up here in the long tail, a rare case that they never encountered before, but they say, oh, well, okay, I never saw this before, but it's similar to something I've done before, and I can adapt what I did here, and I can apply it over here. So that ability to make analogies and see similarities and to adapt a skill is something that humans seem to be quite good at, and robots don't seem to be able to do yet. So just a couple of quotes from some kind of robot papers, overview papers. It's not feasible to pre-program robots for all possible contingencies they may face in human environments. A considerable amount of knowledge needs to be figured out by the robots themselves. And that's definitely what humans do. And this is a very old paper. An ideal system would be able to behave like humans do in these sorts of environments. In particular, it would have to exhibit creativity, devising new actions that can solve a problem or shorten a plan, use analogy to transfer solutions from other problems. So that was in 2001, a paper to do with planning, but it's still very valid today and it still hasn't been solved. So here's another little video. It just shows the skill that humans have in doing manipulations. Why she wants to turn the books around, I'm not sure, but it displays a lot of skill. The way that if you look at the way the books are pulled out, when she pulled out books there, she knows that the other books will fall back behind. That kind of skill is very typical. When you want to pull out books, you put your finger on the top first and pull it out so you expose the surfaces that you can catch better. And you see that being used a lot. So there's a tiny manipulation there that you can see where she uses one hand to push the other book out of the way. Those are the kind of things that cope with situations where things would have gone wrong otherwise. I'm going to skip on a bit towards the end. Right, so she's rearranging some books here. And right, you see when this book is going in, right, it was very quick, hard to see, but the other book, the page was opening a bit. And a human will know from a model, oh, every time I move the mouse, it's jumping. Sorry about that. A human will know that if you persist with that action, you'll just crush the page that's sticking out. So I'm going to just show it again. Right, when this blue book comes out, and you'll see one page is sticking out right here. Actually, I need this to do the pointer. Yeah, so that page is sticking out, and we know from a model we can make a prediction, and that's a very important part of manipulation, to have models of the objects and be able to make a prediction of what will happen. If you push that book right in, it's going to just crush that page that's sticking out. So if you bring in the other hand to pull that page out of the way, those are the kind of little manipulations that help us to cope with the unexpected things that might arise. So that's just a bit about the problem. Like I would like to see robots being able to do those kind of everyday manipulations that humans do and to cope with unexpected situations. So then this work that was done a few years ago, and Pavel helped out, you see his name on one of the papers here. We started off with tools, just looking at, can we make an analogy between similar tools? So the idea is, if you wanted to hammer something, but maybe you don't have a hammer, could you use something like a frying pan as a hammer? And could you get a robot to recognize for some new object, take a 3D scan, look at the geometry of it, and then make a decision about what kind of activity you could use it for? Similarly, if you don't have a screwdriver, you might be able to use a knife like this, a sort of butter knife to turn a screw. And people make very creative solutions. If they need a funnel, they can cut part of a bottle, or they can roll a paper around to make a funnel, because you know the shape that you want, and you can make another object fit that purpose if you want to. So this then is, I hope everybody knows Indurka's theory of projection here. So this is what we used. So just to give a quick overview, this is taking an example of chemistry, where Kekulé discovered this structure of the benzene ring. And the story is that he was, I think, on a bus and he was falling asleep and having a dream about this. I don't know if it's true, but he knew that there's some structure with a chain of hydrocarbons, and he was having some dream about a snake eating its tail. And then he got the flash of inspiration and decided, oh, actually, this might not be a long chain, but might be wrapped around in a ring. So this idea that Bippin calls projection is that you have two domains. You have a source here on the left and a target here on the right, and you impose the structure of the source onto the elements of the target. So here the structure of the source is a ring where the chain is connected back to itself, and then you impose that on the elements in the target domain here, the bonds and atoms. So then you can come up with the idea of the benzene ring like this. So we applied the same kind of idea to see, well, could I see a frying pan as a hammer? So my source is a hammer, I really want a hammer, and the elements I have here are parts of the frying pan, like I have a handle and I have a head, and could I make some mapping between the parts? And I could say, okay, maybe the handle of the frying pan looks kind of like the handle of the hammer, and I need some head to hit with, so maybe I use part of this flat surface at the bottom of the frying pan as the hitting head, and then I should be able to use the frying pan to hammer things. So we worked with point clouds from 3D scanned objects, and we tried various different methods for segmenting the point clouds, and what we did eventually is we just planted seeds in the point clouds and then grew different segments, and then we had 200 segments in a point cloud, and we looked at all the possible pairs and see, was there a good pair there that could be the handle and the head of a hammer. So when we applied it to an actual real hammer, it works well. It says that's the head, that's the handle. It has a model that it's learned about what makes a good hammer, the angle between those, the distance between them, and the size of them. When we applied it to this, which was an electric screwdriver, we were able to get this kind of creative solution. If you wanted to use it as a hammer, you might grab it here, and you might use, there isn't any circle on the screwdriver, but it just imagines part of the screwdriver here could be used as a hitting head to use to hit an object with. So that's an analogy among tools. there are a few other examples as well. The general idea is that there's a search going on. So bottom up, you have some features that you detect from the object, maybe segments in the 3D point cloud. And then top down, you have some pressure being exerted by the task function because you want to find a good hammer. So there's an interaction here between what the world is affording bottom up and what you want for your task top down. Right. So we had a simple selection here of possible candidates, but I think it could be more clever if we had the top-down pressure to avoid a sort of brute force search of all these 200 different clouds, but different segments, but that it could top down say, well, I really would like to find a good hitting head on this side of the tool, so search more on this side. We didn't get around to doing that, but I think it could be done in a more clever way, this interaction between top down and bottom up processes. So some other examples, like we looked at a piercing task and what it would see in a fork, and the same fork then could be conceived of as something to lift things up if you segment it in a different way. This example, like a frying pan, could be used for multiple different things. It could be used like a hammer, or it could be used like a scoop for lifting things up. Or you could use it if you want to reach for something, then you might want to grasp this bowl part, and you might want to reach this part into a gap to retrieve something that's been maybe lost in a gap. Some further examples, this is like an ideal model of a spatula at the top, and then how it fits to some other spatulas, and then even if you try to fit it to a knife, it says, okay, you could use a knife like that, you could grab it here, and you could use this broad head to slide under something to lift it up like what a spatula would normally do. So then we went one step further, and this is where Pavel came in doing this work, where we tried to get the robot to actually execute skills using tools and affordances in the environment. And so with this one here, we just handcrafted a script for what the robot should do, the actions it should do. But the actions then are parameterized by certain key points of where it should move to. And these key points are detected through the 3D vision from the environment. So one of the actions we were looking at here was trying to scrape something off a knife. Imagine you have some butter on a knife or something, some sauce, and you want to scrape it off an edge. So you look for the nearest edge of the target object, and then you bring the blade of the knife onto that edge and you pull it across, and you have to do it in the right orientation as well. So this was the work that was in the robot conference in 2019, but it was done a bit before. So there's a video of this. This is the last video. So this goes through some of the tasks. This is like this scraping task with a knife. So the robot had 4 different phases of motion that it goes through, and whatever object you give it, it will try to do it in the same way. It tries to find what is the most thing that seems like a knife on the surface of the spoon. This one is now scooping, so it tries to use the spoon to scoop something out of the bowl, and it has to adapt to the size of the spoon and the orientation of the head. So it detects the container part with a super paraboloid shape, and then it knows it has to bring that into vertical orientation coming out. And this is some of the examples done in simulation. So this one here with the cup, it wasn't programmed for a cup, it was actually programmed for a spoon, but with the cup it can detect the container part of it and the handle part, and then it can orient it in an appropriate way to do the action. You see some holes inside the cup, so it looks like it's hollow inside. But yeah, so these are some of the simulations were done in Gazebo for the manipulations. We did 5 different manipulations. If you look at a scene like this breakfast table scene, the idea we could call task-driven representation. When you look at that scene, you represented extracting key features depending on what task you want to do. So this is the top-down and bottom-up idea I talked about. So if my top-down task is I want to scrape something off a knife, like I have butter on a knife and I want to scrape it, then I'm going to immediately look for edges. Like this edge of the bowl here, I could scrape something on. This edge here, I could scrape something on. And this edge here, I could scrape something on. I can ignore the rest of those shapes and just focus on edges that would allow me to scrape. If my task was different, if I was looking for a container to hold some liquid, then I will look at these containers and I will consider the container shape of those things, and I will ignore other aspects. If my task is to stack things, like I'm cleaning up and I want to stack up the different plates, then I'll focus on the surface on the top of one and the surface on the bottom of one, and whether I think they would fit together. So the model that you use, the way you would abstract an object, will depend on the task that you want to do with that object. So that's the idea of task-driven representation, which gives it a way to transfer to new scenarios by looking at the geometric shapes in this case. So this actually is present in robotics already. There are a lot of works that represent the world in a way that makes it easy to do the task they want. Some examples here with manipulation, where you just take convex hulls of varying complexities of different parts of objects. You approximate things that's just good enough for the task you want to achieve. There's another, this work was quite famous at the time, where they were folding clothing, and they just represented clothing as being completely flat. So whenever it folds, it's completely flat. Then there was a different robotic work where they were doing a robot who was ironing, and he was measuring very carefully the surface geometry and when there was a ripple on the cloth that needed to be ironed out. So what you abstract, what you throw away, and what you focus on depends on the task to be achieved. This shoemaker obviously would need a 3D version of the material, not like the flat cloth over here. So that just shows that in a lot of work, people are doing this idea of task-driven representation, but the robot doesn't do it themselves. The human designs the representation, and the robot is made to do one task, like the clothes folding robot. But what we need to move towards in future is that the robot would make its own representation, depending on the task it wants to do at that time, and it will decide how it wants to abstract the objects driven by the needs of the task. So that's that work. So another idea that's not implemented, but is a future hope, is to transfer skills. So if we take this skill, like pulling books out of the shelf, a typical way to do it is to pull on the top first, and that exposes the surface at the sides so that you can get a good grip on the book. Now, this is the kind of skill that you could potentially transfer to a lot of other situations. So think of this then like a child's game, where you've got this skill and you want to apply it in lots of different scenarios and see how could it apply there. So for example, in this scenario, could we apply that kind of skill? Potentially, we could push on the slice of bread here and tilt it upwards if we want to lift it, because there's a surface at the back. So this is like changing the orientation from where we pulled the book downwards. We could now pull the slice of bread upwards. If we want to take out these cans, we could treat it just like the book, even though the can is circular. It's not rectangular like the book, but we could pretend it's like rectangular, put a finger on top, pull out the can, and then get access to get a grip around the can and take it out. What about this situation? It's quite hard to move that box because we can't get around the other side. But if we push one finger on this side, we could pull the box out this way, or we could rotate it up this way. So it's applying the same kind of skill as the book, but in a different scenario. Here's another case. If I want to lift up a pizza, it's hard to get under the pizza when that underneath surface is not exposed. But if I push on the edge of it, I could potentially tilt it upwards. So this would be a transfer of the skill that was learned with the book to some different scenarios. And how could we do that? We need something bottom up. We need some features. So in this case, it looks like the surfaces would be important features. So we detect the surfaces in our source scenario, and we detect the surfaces in our target scenario. And then we have to look at different surfaces. So initially we might think, okay, here I pushed on the top of the book and I rotated. So I should push on the top of the pizza and rotate, but that won't work. So we need to consider mapping it in a different way. If we push on that side, and then which way to rotate, there's only one way free to rotate in order to lift the pizza box up. So what this requires then is something to be detected bottom up from the world. So I talked about surfaces with the pizza boxes. In general, you have various different, I could call mid-level features, like apertures, edges, corners, concavities, that can be useful, and there are more than those. And you get those features bottom up, and then you do a search for some source skill that you want to apply. You search, how could I map it to what I've got in the situation that's in front of me? So again, it's the same kind of idea using Biffman's idea of projection. Instead of having a hammer here, we've got this source skill. And instead of having a frying pan here, we've got this target scenario. And we want to see some way we can make a mapping from the relationship among the features here and how we did the manipulation over to the new situation we've got here. And we're going to need some interaction between top-down and bottom-up process and some search process that will try to find a mapping between the needs of the task and what's offered by the environment in the new situation. So if there's a take-home message out of this, I think that we need this interaction between the raw data, like in this case, it's robot vision, what the camera is giving back, and the task needs. There needs to be some interaction to find a mapping for how you apply a skill. So I'm getting to the last part here. And so I said analogy could be used for finding similar tools, and it could be used for mapping a skill onto a new situation. But a third place it could be used is to model what you're dealing with. So when you push a spatula under a pancake, what is really happening there? Why does the spatula get under the pancake, and why does it not just push the pancake along? Well, if the spatula is too fat, it would push the pancake along. So we may possibly model it in our mind as something like this. We model the spatula as a narrow shape, and we model the pancake as a fat shape, and we know that if we push that in, so this is us modeling in our mind in terms of things that we're familiar with, and we know that pushing that in will cause this rounded edge to rise up. And if we have the problem that the spatula is pushing the thing along, then maybe either the pancake is too low down or the spatula is too fat to push it along. So this seems to be something that humans do a lot. We model things in terms of things we already know. There's some examples from Piaget's observations of his own children as well, where the children find something with a toy and it gets stuck on another one, and then the child tries to understand that in terms of something they already know. So the child gets their own finger and pulls their own finger on things to understand, okay, the finger in that shape could make a hook, and a toy in the same shape could have the same effect. So it's something we do frequently. I mean, in scientific discovery, we try to model electrons and atoms like balls spinning around because it's something we're familiar with, or like waves, again, something we're familiar with. So we model the unknown in terms of things that we know. So this is another role for analogy. So this is from Biffin's work, where he had this example of painting, where people were trying to model the process involved in painting because they were trying to make a new synthetic paintbrush. And it shows that sometimes the model could be quite elaborate, I guess. So in this case, they initially tried to model painting as scratching paint off from the paper, so the paint is getting rubbed off. And that didn't work. It didn't give the right predictions. So then someone came up with the idea that painting should be modeled as a process of pumping, that when the paintbrush is getting bent, it's actually pumping out paint. And that kind of model worked better. So it just shows that sometimes the model could be, I guess, surprising or somewhat elaborate. And here's another one. If you think, how would you model a sponge? How does a sponge work? How does a child think about a sponge? Possibly, the child would think about it as lots of little containers that can get filled with water and that can get squeezed so that the water comes out. So I wanted to find some kind of picture of a flexible container. That's the best I could come up with. But what seems to happen here is a sort of a reverse projection, because the other times I showed you this projection diagram, I had on the left the ideal model and on the right the thing that you're really presented with in the world. And here it's in the reverse, because this is the thing you're seeing in the world. You're seeing a sponge and you're trying to create a model of it. So you're not just finding parts of a frying pan, you're actually trying to create an imaginary model of that sponge in terms of some components that you're familiar with so that you could make sense of it. A similar thing happens in electrical engineering. People often imagine electric circuits as like water flowing in pipes. So the real thing you're dealing with is an electric circuit, and you project it onto the components of pipes with restrictions in the pipe or with a heavy propeller like an inductor. So you rearrange the components of water and pipes to match what's happening in the electric circuit. So that's why I call it sort of a reverse projection compared to what we had before. But that seems to be what's going on when people model things in the environment. And again, it's this process fitting between bottom up and top down processes. And robots need to do that. When you deal with manipulations, you need to model the objects you're dealing with. And sometimes there are unseen things. There might be some object is getting stuck on something. You might imagine, oh, maybe it's hooked on and I can't see behind and I need to slide it off before I can get the object free. So that's what the humans do when we look at those videos. They do make models of the objects they're dealing with. So that's another role for analogy, is to make those models. So I think that brings me to the end. The last one is just the long tail. That you might think, okay, why do we need all this elaborate idea of having a model of a sponge in terms of lots of little containers? I mean, I could just give the robot a model of a sponge that makes the right predictions about how a sponge will soak up water, and if you squeeze it, the water will come out again. But the whole idea here is that you want the robot to deal with things like a sponge when it's a rare case that it hasn't been trained for. And that's what humans do as children. They're learning about new things that they haven't been trained for before, and they're trying to relate it to something that they've been trained for before. So that's why you might want to use analogy to tackle these long tail cases that occur frequently in aggregate, but rarely individually.